David Weiss from Conning is going to, as a similar case study, and then we'll break and eat and drink the rest of the food.
I'm not sure I'll call it a case study, but I'll tell you a little bit about my experiences. Just a little bit about me. I was not a computer science major. I was an economics major. I did take 2 really good computer science courses that kind of sparked my interest. And I quickly got involved in the finance industry after graduating college. And I've been in that industry for almost 4 decades now. And so it's been through many, many changes and continues to evolve. But I got my start at Morgan Stanley in the early part of the 80s, and I've always sort of been at the intersection of sort of the math, finance, and technology, and have been living the problem that Julia Computing has solved for this entire time. It's always been a case where performance is critical. Whatever it is you're doing, I mean, there's no limit to the amount of CPU power finance industry can consume in terms of modeling exotic products and the like. But productivity, time to market have always been critical as well. And so that's been my experience. And at Morgan Stanley, we solved that to the best way we could with a language called APL. How many people even know about APL? Okay.
I'm so sorry.
Some people with gray hair. Well, so APL was the best solution that we came up with at the time to solve this problem, especially in this sort of mathematical kind of space, because APL had the sort of those good parts of the interpretive, quick to develop. Granted, it was the most unusual syntax and of a language and the like, but it was an interpretive language, but it was vector and array oriented. So if you can express your problems as array problems, then you can actually achieve close to Fortran type performance, because if you're adding or multiplying large arrays and vectors and the like, the interpretive overhead gets amortized over those vector lengths. And so you're actually able to achieve some pretty good performance. And that was the best solution. All of Morgan Stanley's analytics were based on APL through the 80s and into the 90s. And it was all mainframe based for most of that time. This is before, personal computers, the PC was just coming on the scene. And so it was, and then I guess it was sort of about the late 80s came the Unix workstations from Apollo, God rest their souls, and Sun, which had a better run. And when we made that switch, which is an important switch, because if you're talking about massive computing and price performance, the mainframes were just not where it was at anymore. We had to get to these Unix workstations. And so we said, okay, we'll just take our APL code and we'll go buy an APL compiler for Unix workstations. And unfortunately, all those APL interpreters, did I say compiler? APL interpreters kind of sucked on that platform. And fortuitously, I met a guy named Arthur Whitney who said, oh, I can write you a good APL interpreter. And somehow I convinced the senior management of Morgan Stanley to let us write our own language. And we did, and it was called A, because Arthur's into brevity, and eventually became A+ when we integrated a full motif-based UI to it. And that solved the problem and actually did better. So in terms of what we were getting out of the hardware, we were doing better than we were, pound for pound on the mainframes. And Arthur went on to develop a next generation language called K, and then became KDB, which is still quite popular in the finance. How many people use KDB? Anyone here? Yeah, okay, we got some KDB people. So So yeah, so anyway, that's sort of by way of background. Then around the very end of the 90s, I got involved with the insurance industry and came to the industry with a bunch of other people who had Wall Street backgrounds, and found that the insurance industry was very far behind, I should say, in terms of the ability to understand and manage risk. And we came upon the concept of Monte Carlo simulation and what was called dynamic financial analysis as the way to sort of solve the problem for insurance companies. And I founded a company with some peers right around, I think it was the very end of 1999, with the goal of developing, best-in-class dynamic financial analysis software for the insurance industry. And again, I needed performance and I needed productivity. And so I went with Arthur's current language called K and built up a platform, and that worked. So the key thing with these array-oriented languages to achieve performance, what you need to do is always be able to operate on vectors. And since Monte Carlo simulation involves many iterations of the Monte Carlo, many different trials, whatever you want to call them, we said, okay, that's a vector dimension that will always be there. So we'll vectorize on this scenario or iteration dimension. And that worked pretty well. In fact, very well for quite some time. But then in 2003, there was this sort of cataclysmic event in computing, at least cataclysmic from my perspective, because throughout my whole career until 2003, every 18 months or so, the computers just got twice as fast and could do twice as much. And that came to a screeching halt at around 4 gigahertz clock speed in 2003. And from there on out, it's been, no, we'll just give you more and more of these CPU cores, but we're not going to make them any faster, really any more capable. And this posed a problem for me because really that in combination with cloud computing, where you can rent a huge amount of computing resource for a very short period of time, right? So clearly the way of the future for this kind of large-scale Monte Carlo simulation is if I've got 100,000 scenarios I got to run to get a good distribution of outcomes, I want to run it on 100,000 CPU cores and get my answer very quick. And I want to rent those 100,000 for a very short period of time. And of course, all that technology is there. But wait a second, my vector dimension just vanished from me if I'm going to remain competitive in this business. So around 5 years ago, roughly, I lose track of time, we set out to come up with a next generation architecture. And we knew our programming environment wasn't going to cut it. And right around that time, it was pretty fortuitous. One of the guys that worked for me had read an article in Wired magazine. I'm sure you guys remember which one that was. And this guy, Christian, came to me, he says, there's this new programming language, Julia, which may solve our problems. And as they say, the rest is all history. So we got involved very early. So we've been through the breaking changes ad nauseum. I think we started with 0.4, maybe. I think it was just coming out of 03 and into 04. But it was clear that this was the best solution. We looked at other languages out there, but nothing else really delivered on the promise that we needed. And so, yeah, I took a little bit of a gamble, and I had to talk to my management and, about why we were doing this. But it's been a really, really good ride. And it works. And yeah, there were some growing pains, and I thought January of this year was our month to convert from 06 to 1.0, and in May I think we were really done. But but we got there. So I sort of recap, what I like most about Julia. It's the speed together with the productivity. I mean, that's sort of the main thing. What's really cool about it is it's really extensible, and it's extensible maintaining performance. And that's the evidence of that is how much of Bayes' Julia is written in Julia, right? Most of it is written in Julia, and you can just extend the language with your own types. You can extend the base functions to operate on your types. So I can define plus for my new types if plus makes sense. It's easy to learn, although mastery takes some time, at least for an old guy like me. And it's a really great community. And I'm sure that's true of many communities, but I've been to every JuliaCon since, not the first one in Chicago, but everyone since. And I just love the community, and people are really smart and they're contributing really good packages. And then the other thing is I love the fact that it's free and open. And I think that's the way to go. It's not completely free. I do give these guys some money. And when I call for support, I get really, really good support. And so I appreciate all that. And that's it. And, with some historical perspective, every decade gives us 2 to 5 programming languages that, survive the test of time. In the 50s, it was Fortran and Lisp. The 60s, we got BASIC and COBOL, APL, ALGOL, PL1. The 70s gave us C and Pascal, Ada, Smalltalk. Then we started to get these languages like SAS and MATLAB that were becoming a little bit special purpose. In the 80s, we got Python and C++, Perl, Objective-C, and then Wolfram came up with this really cool thing, Mathematica. 90s gave us Java, JavaScript, Visual Basic, Ruby, maybe Haskell, OCaml. The 2000s, what did we get? We got Scala, C#, Groovy. It's too early to tell whether or not those are going to withstand the test of time. And then what about this decade? So if I had to place my bets at the languages in this decade that are new, introduced in this decade, that are going to survive the test of time, it would probably be Swift and Go, in part because of the huge companies behind those languages, present company included. Rust maybe, and for sure, I'm betting on Julia.